again for today's video in section 2.3, the derivative function from the textbook. Please remember while you're watching the video to take down any important notes, and please feel free to pause or review the video or rewind the video at any point. Don't forget to submit your online whisk, which includes your summary of the video as well as an important question. Moving on. So we've been dealing with derivatives, and we're going to take a look at a way to determine the derivative in more than one format. The first format we're going to look at it graphically. So let's say I have if you remember, the point is the slope of the tangent line at that point. So if I have a graph of a function that I want to find the derivative of, then all I have to do is little mini tangent line segments at each of these points. And after I draw the mini tangent lines at each of these points, then I can calculate the slope of the tangent line, and I will get different values for the different points. But I want to point out here that it's going to be impossible to get more than one slope value of a tangent line at one point. So basically, for every x value, one derivative value at that point. In other words, there's going to be at most one slope value at that point. Well, that seems to be very much like the definition of what makes up a function. And actually, the derivative is a function of x, because for every x value, there's a corresponding, at most there's a corresponding y value for that x value. So the derivative is a function, and it is a function of x. And to determine what the derivative function is, we use the definition of derivative, which is, and with the derivative function, we're going to call it f prime as notation, or g prime depending on what the name of the function is, and it's the rate of change of f at x. And we know that is computed as the limit as h approaches 0 of f of x plus h minus f of x all over h. And that's what we learned last time. And so that's how we define the derivative function. So now that we know how to define a derivative function, let's take a look and determine what the derivative function is for the graph that we started off with. If you remember, the graph of the original graph looked like this, and we were finding the slopes of many tangent lines at that point, and to come up with their values. Once we determine the values, we can plot them as well on, in this case, on the same graph, and we end up with a graph that looks like this. So in yellow, this is the derivative function of this graph, because as you can see, the slope values of these tangent lines correspond to the y values of this graph. So that's good to know. It is quite tedious, but the derivative graph also tells us more than just the slope of the tangent lines at that point. It also tells us some other information, and that information is what we're going to take a look at. So let's say, as you can see here, that the slope of the tangent lines seem to be increasing, or the slope of the tangent lines seem to be positive here and here, and positive here and here. So it seemed like on the interval from -2 to -1.5, our slope values are going to be positive, and on the interval from around 3.5 to 5, our slope values are going to be positive. And as we can see here, the derivative function is positive, i.e. above the x-axis at these points. And then the slope values are negative from -0.5 to about 3.5, which is consistent with our graph, because as we can see, our derivative graph is below the x-axis from -0.5 to 3.5. So a way that you can check to see if your derivative function makes sense is just checking to see that the signs, or where it is above or below the x-axis, is consistent. So we can say that if f prime is greater than 0, then that on an interval, that means that f is increasing over, and if f prime is less than 0 on that interval, that f prime is decreasing. Moving on. So we look at derivative of the graph graphically, derivative function graphically. Now let's estimate the derivative function numerically, and that is even more tedious. So let's say I have, from example 3, different values of concentration of a drug in the bloodstream over time. And as we can see, this value is based off time, so our x-axis really is t-axis, and our function axis is really c-axis because we base off concentration. And as you can see, the values in t are changing at 100th of a minute. Okay, very close. And if we assume that there's nothing funny going on in that 100th of a minute, then this is a pretty accurate table to represent the function. But since we're trying to estimate the derivative, we need to look at what's happening, what's the rate of change over each of these intervals. And we're looking at how y changes as x changes, in this case by 0.1. And as you can see, that it seems like in the same sense, we're having some type of positive change here, here, from here to here until we get here. And then we seem to be having some type of negative change as we go from here, here, here. I want to point out an important point right here between 0.4 and 0.5. It looks like there seems to be no change. So that would tell you that the rate of change at this point, it seems to be 0. And then if we take a look over here at the change over here, you see the biggest decrease seems to be between 0.9 and 1.0 minutes, whereas the biggest increase seems to be at between 0 and 0.1 and 0 and 0.2. This is about 0.5, whereas this is almost a 18-point decrease. So based off this information, it seems like our derivative graph will be positive between 0 and 0.4. It's going to be around 0 at 0.4, 0.5, and then it's going to be negative below the x-axis from 0.5 on. If we take a look and we actually estimate the slope of the tangent line, we just find the average rate of change at these points. These are the values that we see, and it's pretty consistent with what we said, positive up until this point. And then we get to this point where it's 0, and then it's going to be negative from this point on. So these are the exact values. So when I graph it, it's going to look like this. And as we can see here, this was where it's positive. I'm sorry, that's the C function. I apologize. This is the graph of the original concentration function. These are, so if I were to graph the slope, the derivative function on the same graph, as we can see here, this is my crude attempt at a drawing based off these corresponding values. And it would look something like this. I'm sure it would look better if someone else drew it. So we looked at calculating or estimating the derivative of a graph from a graphically, and we also looked at it estimated numerically from using table values. Now we're going to take a look at derivative function from a formula. And for certain formulas, well, you're going to have to memorize a lot of these formulas. It'll make life a lot easier. But some of them are kind of intuitive to understand. So for example, let's take a look at the constant function. As we remember, the constant function is a horizontal line where the slope is 0. So it seems like no matter what the horizontal line, where the horizontal line is, the slope at each point of the tangent line is always going to be 0. So the constant function's derivative is always 0, the constant 0 function. A linear function, we know, has a constant slope, which doesn't necessarily mean 0. So that means the slope of the tangent line at that point is going to be that same slope value. So for any linear function, the derivative function, or f prime, is going to be the slope value. So it's also, the derivative function is going to be a constant function for when you have a function being a linear function. I know that was confusing. The derivative function of a linear function is going to be a constant function because the slope is of the tangent line is always going to be the same as the slope of the original line. And last but not least is the power function, which we looked at the derivation in class the previous day. And as we can see here, that whenever the power function is of the form x to the n, then the derivative function is of the form n times x to the n minus 1. And through this unit, we'll be looking at more formulas for different types of functions to find the derivative.